Excuse me, can you hear me?
Yes.
Okay, fine. Assalamu alaikum.
Welcome.
So we started last time to talk about the concentrating collectors, and a part of what we have discussed in our previous class was talking about the thermal performance of these collectors. And as we did for the flat plate collectors, we're looking at the parameters that express losses from the collectors. Problems with these collectors is that they have higher temperatures, and because they have higher temperatures, though we expect them to have higher losses. That's why the surface of the receiver is always less in area so that we can control the losses. Here we are trying to look at the kind of losses that we have, and you'll find that we have some similarity of the analysis if we compare it to what we have done in chapter 6 with a flat plate collector. As an example of the calculations of thermal losses, we are considering the loss coefficient UL and the removal factor as well. Here we have losses from the receiver surface are being as losses to the surroundings in terms of convection heat transfer. First term in equation 731 on the right-hand side, it has a heat transfer coefficient into a temperature difference. This is Newton law of cooling. And the HW here can be determined by the way that we have studied in chapter 3, like determination. This is external flow over a surface. So we determine what is the Reynolds number. Prandtl number might be needed. And then we get the correlation for the Nusselt number from which we can get the value of the heat transfer coefficient or HW. Second term is talking about radiation losses to the surroundings that we call it the radiation losses to the sky. And the third one is the conduction losses through the material, the stand, which is carrying the collector, and the conduction losses through the kind of material. Both of them were combined together, heat transfer by convection, by radiation, and the overall heat transfer coefficient, which is mainly conduction. And they are all making up what we call the UL, or the loss coefficient, heat loss coefficient. And the expression of HR, which is the linearized radiation coefficient, is being given here in equation 732, which is again a way to represent, to avoid the high order of temperatures and try to represent radiation in a form which is somehow similar to the way that we represent convection, but the HR is not a heat transfer coefficient by the physical meaning. It is just an analogy to reach for an expression similar to what we do in convection analysis, and that leads to some sort of a simplified way of writing the equation. Sometimes you cannot get a single value of the UL because temperatures of the surface are not always uniform, but there is a large change of temperature. For that case, what you can do is just as if you are going to divide the system into different parts, and each part would have a certain value of UL. This is for the detailed kind of analysis that will be applied. In case the receiver is having a cover, then we're going to consider here a three set of equations. The first one of them is talking about the losses between the receiver and the interior surface of the cover. And the resistance here is being given in conduction and convection, which is represented in the first term through a conduction relation and using an effective thermal conductivity, and radiation, which is the second term of right-hand side of equation 733. So this is radiation from the receiver surface to the inner surface of the cover. The next equation is talking about conduction resistance through the glass, for example, from the inner diameter to the outer diameter of the cover. So this is basically conduction heat transfer through the cover material. It is cylindrical in shape. And the third equation is taking care of, again, the convection and radiation to the surroundings. Convection to the air from the outer cover temperature and radiation to the surroundings or to the sky from the outer surface temperatures. As we talked about that last time, then this is assumed to be a one-dimensional analysis. So the Q loss in expression 733 is the same, Q loss in 734 is the same as 735. So it's basically kind of energy transfer from the surface of the receiver to the surroundings. And for one-dimensional analysis, this is the key for solving the problem, to have basically kind of assuming heat transfer rate, which is going through the material, and then you are going to account for the resistances that it is facing in between. Back to equation 733, the K effective that we have here basically is taking care of conduction and convection, so that the K effective can be given here. This equation is obtained from chapter 3, and it's a maximum value between 1 and this expression that has Rayleigh number n, which is taking care of the natural convection. And this is the Rayleigh number, which is, or the modified Rayleigh number, which is used for this equation. It's an iterative way to solve the problem. We start with assuming a value of the temperature, which is basically Tc outer, which is in this equation, it is this value. You assume a value of Tc outer. And if we are talking about temperatures that we have a receiver temperature, inner surface temperature, and outer surface temperature. So we're going to start with the outer surface temperature to be assumed. And basically, this is going to be less than the inner temperature, less than the TR, so it is closer to the air temperature. So we assume it as a value which is somehow close to the air temperature. Then we assume this value. From this assumption, we can calculate Q loss in this equation. Use this value of Q loss, substitute it in equation 734, and calculate the inner value of TCI. Use the inner value of TCI in equation 731 and calculate a value of Q loss. Compare Q loss that you obtained here from Q loss that you obtained from equation 735. If they are close enough, okay, solution is accepted. If they are not close enough, you need to repeat it again by assuming another value of TCO and keep on trying until the solution converges and you get a final answer. This is normally being done whenever we are talking about hand calculations. In EES, what you have to do, for example, is just put the three equations and put the information that you have and let the temperatures be calculated iteratively, automatically by the program. Let's look at an example. The example is asking for the calculations of the heat loss coefficient for a receiver who is having a diameter of 60 millimeter. It is at a temperature of 200 degrees Celsius. The absorber surface has an admittance of 0.31. The absorber is covered by a glass tube. So we have a glass cover here, which is 90 millimeter in outer diameter, 4 millimeter in thickness. The space between the absorber and the cover is evacuated. So we are eliminating conduction and convection losses in between the receiver and, or in the space in between the receiver and the cover. The outside wind speed is 5 meters per second, and air temperature and sky temperatures are considered here as 2 degrees Celsius for the sky temperature and 10 degrees Celsius for the air temperature. So, as we have just mentioned a while ago, we need to go through that set of three equations to be solved together iteratively. But before we do that, we need to estimate the value of the heat transfer coefficient by convection from the outer surface to the surroundings. And this would require that we would know what is the value of Reynolds number that's being calculated here. Rho is the density of the air, 1.232. 5 is the wind speed, and D is the diameter of the cover. And mu is the dynamic viscosity of the air. So substituting here, we get a Reynolds number of 30,900. This is laminar flow. Remember, we are talking about external flow, and the external flow, the flow remains laminar up to values. The books have differed in the values, but it is somewhere between 300 and 500,000. So this is definitely laminar flow for that case. The 2000 is only for internal flow. This is just a reminder. Knowing the Reynolds number, we are going to use the correlation for calculations of the Nusselt number. And the Nusselt number is being calculated here as a function of, we have a constant and we have Reynolds number to the power 0.6. And this correlation again is obtained from chapter 3 for the calculations of the Nusselt number, and the Nusselt number is 148. Substitute by the defining relation that Nusselt number is h into the diameter divided by thermal conductivity of the air. Then we are getting the expression of H, the heat transfer coefficient here, 40.5 watt per meter square centigrade. Now, having the value of HW, which is now can be substituted in equation 735. Remember, we start by equation 735, assuming a value of TC outer. And the assumption that has been done here is assuming a value of 290 Kelvin for the TC outer, the outer surface temperature of the cover. So this is the assumption that we made. We substitute in equation 735, and we get an estimate of the value of 99.5 watts. All the parameters that are needed are given. Outer diameter of the cover is 90. The L is 1 meter. HW has just been calculated, and the value is 40.5. The temperature difference is basically this assumed temperature minus 283, which is basically the air temperature, 10 degrees centigrade. And then this is the emissivity of the glass. This is 5.67 into 10 to the power of minus 8. It's Stefan Boltzmann constant. And again, temperature to the power of 4 minus sky temperature, which is 2 Celsius. That is 275 Kelvin to the power 4. When we do that, we calculate the value of Q loss, and the estimate here is that Q loss is 99.5 watts. Then we are going to go to equation 734 for the calculations of the inlet or the inner surface temperature of the cover. So Q loss has been calculated from the previous equation. We substitute here with our target is to calculate the value of TCI. In this expression, we have calculated the value of TCI to be 291.1 Kelvin. Now take this value and substitute in equation 733, and this is going to be for the calculations of the Q loss. To remind you again, this is what we have done. We started by equation 735. We assumed the value of TC outer as 290, and then we calculated Q loss. We took this Q loss here to calculate the value of TCI. We got the value of TCI. We substituted in this equation to calculate the value of Q loss and compare the values. Having done that, the value of Q loss that has been calculated has been estimated, or the value is equal to 137.8. What was the previous one? It was 99.5. So according to our assumption, we get a 99.5 watt. And then when we continued with the equation, we got this value. They are not close, which means that we need to reiterate again by changing our assumption from 290 to another value. What has been done here in the steps is the value have been calculated, and assuming a value of 295 instead of 290, that has resulted in another value or a new value which is not close. Actually, our first step, our first estimation, we got a value of 99.5 from the assumption of TC out, and then we substituted back to get TCN, and from TCN we got a value of 137.8. They are not close. The difference is this one, the calculated value, is greater than the equation or the value obtained from equation 735 by about 38.3. So what we did as a second iteration, instead of 290, we used 295. That has led to an expression which is having a difference. Instead of plus 38.3, the difference is minus 27.8. So the second iteration also did not work. So what has been done here? One of them, the difference is in positive, the other, the difference is negative. So what we did, we took some sort of an average value in between, like doing a linear interpolation to see what would be the value between 290 that we assumed initially and 295 that we assumed later. One of them resulted in a value which is higher, one resulted in a value which is lower. So why don't we make some sort of an interpolation and pick a value in between the 290 and the 295? So the linear interpolation came up with this value, 292.9. Substituting this value, we could get a value of Q loss equal to 136.7, which is converged between both of them. Accordingly, the value of UL in this case is the Q loss that we have calculated divided by pi into the diameter of the absorber into the length into the temperature difference that we have here between the two values. Accordingly, an expression of the overall loss coefficient of 3.82 has resulted here. So this is a case which is showing that the UL is sensitive to the changes in the assumed value, or the temperature variation are resulting in significant changes in the value of the losses and the corresponding value of the overall loss coefficient. This figure is showing the dependence. As you are changing your assumption, then the value of Q loss can change significantly, going from a receiver temperature of 300 to 350, the temperature is changing, or the overall loss coefficient is changing from something like 0.75 to a value of maybe 2.1. So there is significant change here, and it becomes more sensitive to variations in temperatures. In this example, we have assumed the annulus to be evacuated. So the issue of K effective and so is not considered in the equations because it's basically vacuum and the only kind of loss inside, which is, it can be mainly done by radiation. What if the space between the receiver, which is cylindrical in shape, and the cover? So in the example that we solved, this kind of annulus right here is evacuated. What if it's not evacuated? Actually, that means that the equation needs to be solved again. We solved it previously and we got, with the vacuum, the value of UL, or the overall loss coefficient, is 3.82. If we do that, considering there is air in between the two surfaces, then it is going to lead to a loss coefficient of 6.868. You see, it's close to being twice the value of the loss coefficient, or the losses are going to be doubled if we consider that it's not evacuated, but there is air inside. So definitely evacuation has resulted in about 50% reduction in the losses due to the non-existence of convection heat transfer, for example, for the air. What we need to do next is to consider the fact that temperature all over the absorber, all over the receiver, all over the cover is not constant. It may vary from one location to the other, and the variation is not trivial. It's actually considerable temperature gradients are expected. So we need to come up with a total loss coefficient that would take care of basically the losses in the inner side, which is basically from H heat transfer coefficient for the inner side, for the inner surface, as you can see it here. So this is taking care of convection inside, and this is conduction through the material from the inner to the outer. And this is the loss coefficient that we got. So an overall loss coefficient can be calculated here, similar to what we have done in the case of flat plate collector. So we're going to follow the same way that we have done with, or the same methodology in general that we have done for the flat plate collector to come up with an overall heat transfer coefficient. The inner and outer diameters of the receiver are basically di and the outer, and HFI here is representing what? Convection heat transfer coefficient between the fluid which is passing inside the receiver. So we have a receiver here. This receiver is supposed to be heating a fluid from an inlet temperature to an outlet temperature. And as it's moving here, it transfers heat by convection with the outer surface. The outer surface is hot. This has been heated, which is our receiver. And inside there's a fluid which is passing. So this fluid is to be heated. So heat transfer by convection from the surface to the fluid is going to occur. And the heat transfer coefficient in this case is HFI. Then this absorber is having a certain thickness, so there is conduction losses across the thickness. And after this, from the outer surface of the receiver to the outside, we have the loss coefficient that we have calculated in our previous example. So now we are going to make use, or we are going to build on what we have done previously today, to come up with what is going to be the overall loss coefficient from the whole system, so that we can bring the fluid temperature into the picture and being able to see this is the inlet fluid temperature, this is the amount of energy falling into the collector, accounting for the losses, what would be the exit fluid temperature? How can we, or how effectively we can heat this fluid in? And this is leading us, similar to what we have done earlier with flat plate collector, to the expression of useful heat transfer rate. The first term on the right-hand side of the equation is talking about the energy absorbed by the receiver. The second term is talking about the energy losses from the receiver to the outside air by convection and radiation. AA is the shaded area of the concentrator. We have a concentrator, and the concentrator actually can be shaded by the receiver itself. Remember, we have a concentrator. Let's assume that the concentrator itself is looking like this, and we have a receiver here, and the sun is there. So there'll be some sort of a shade in a certain area here. So the effective area is the unshaded area, which is the one which has been expressed here as AA. So this is the unshaded area of the concentrator aperture. AR is the area of the receiver itself, which is P d outer L, assuming that we have a cylindrical absorber. So the kind of energy transfer that's going to be accounted for here is T of the receiver minus the fluid temperature divided by the area, multiplied by the area divided by the resistances that we have. And we have a resistance by convection from the fluid, or between the fluid and the walls, which is this. And because the receiver is having a certain thickness here, so there is conduction resistance in between. So this is the kind of expression of useful energy that we are going to have for the collector. Now, this useful energy is going to be also expressed, as I indicated earlier, in terms of the F dash. So we're going to come back again to the issue of the efficiency of the collector. This expression of S usually is the absorbed energy, and the other one is a representation of the losses from the collector. F dash is given here as an expression of 1 over UL over 1 over UL. UL is the loss coefficient from the surface of the absorber to the outside, the surroundings, and the other two materials, the other two parameters are taking care of the losses between the fluid and the outer surface of the receiver. So this is basically convection resistance here, and this is the conduction resistance across the walls. So as if the whole term here is taking care of the overall loss coefficient. And you can see here it's given in that term actually that it's U naught over UN. U naught is the overall heat transfer coefficient. Now this is somehow putting the equation in a similar manner to what we have done earlier in flat plate collector. QU is going to be given in terms of FR, area of the aperture, and then the absorbed energy minus the losses that we have for the collector. F double dash, which is somehow to the collector flow factor, is given as FR, that's been calculated here over F dash. And then this is given, if you remember, when we solved that last time and said that we have a heat exchange, so there is an effectiveness of the expression, and from heat transfer, the effectiveness might be equal to the value of 1 minus exponential of the number of transfer units. So this is basically the similar kind of expression to what we have done with the flat plate collector. Now let's have an example that shows how this kind of concentrated collector can be used in heating the fluid, and how we would be able to estimate the heat transfer rate, the useful Q, and the outlet temperature from of the fluid leaving the collector. So a cylindrical parabolic concentrator with a width of 2.5 meters, a length of 10 meters, has an absorbed radiation per unit area of 430 watt per meter square. So this is the falling energy from the sun, 430 watt per meter square. The receiver is a cylinder that has an emittance of 0.31. It is surrounded by evacuated glass cylindrical envelope. So we have a receiver which is surrounded by a cover. The absorber has a diameter of 60 millimeters, similar to the previous example. The transparent envelope has an outer diameter of 90 millimeters, similar to the previous example also. It has a thickness of 4 millimeters. The collector is designed to heat a fluid. The fluid enters at a temperature of 167.3 Celsius and at a flow rate m dot of 0.0537. So it seems that this is a collector that is used in a whole array of collectors, so that the temperature would enter at a certain value, it will increase, and as it leaves one collector, it will inlet to another collector where it will be further heated, and then leaving the second collector, getting into a third collector, and so on. So that when it reaches to the collector that we have in hand, the inlet temperature is already 176.3 degrees Celsius. The heat transfer coefficient inside the tube, HI, is 300 watt per meter square. The overall loss coefficient is already being calculated. And if you remember, we did that in the previous example. So the value of the overall heat transfer coefficient we calculated in the previous example is considered here, 3.82 watt per meter square, assuming that the location between the two surfaces, the absorber and the cover, is evacuated, if you remember the number. The tube is made of stainless steel with a thermal conductivity of 16 watt per meter centigrade or Celsius, with a wall thickness of 5 millimeters. The ambient temperature is 10 degrees centigrade. What is needed here, as usual, we are looking for the useful gain, kind of useful energy that has been transferred to the fluid in the collector, and what is the outlet fluid temperature. So this is a typical or a direct substitution to the section that we're looking at or that we're discussing a while ago. The solution is based on equation 7312. Equation 7312 is this, so which means that this is the equation that we are going to rely on for the calculations of the useful energy. So we're going to look at what are the missing terms so that we can calculate. Area of the receiver is pi dl. The receiver is 0.06 in diameter, so its area is basically pi into 0.06 outer diameter into the length of the pipe, so 1.88 meters square. The shading is going to be considered, and we said AA is the net or the unshaded surface area. So the effect of the shade here is going to be considered, and the width is 2.5. The outer cover diameter is 0.09. So we're going to subtract this from the width multiplied by the length. So we get an area of 24.1 meters square. This is the unshaded area. Then the expression of FR to be calculated. We start by F dash. F dash is by equation 7310, and the equation is given here. I'm just putting it here to remind you. Basically, the value of UL has been given in the example as 3.82. That's the value. Outer diameter is 0.06. HFI, it is said to be 300, given in the example. Inner diameter is DI. DI is the outer diameter minus twice the thickness. The thickness is 5. So 0.06 minus 0.01 gets the 0.05 inner diameter of the receiver, as you can see it here. And then D outer over 2, thermal conductivity, it is made of stainless steel, thermal conductivity is 16, and then Len outer over inner diameter. Doing that, we get a value of F dash as 0.984. Then the sort of number of transfer units expression which is needed for the calculations of F double dash is given here. M dot 0.0537, it is given. CP of the fluid, 3260 joule per kilogram Kelvin. And then AR, we have calculated it, area of the receiver, overall heat transfer coefficient or loss coefficient given, that's the same value that we used here. It is expressed here, and F dash is the value that we calculated in the previous step. So that we can calculate the value of F double dash as this number of transfer units into 1 minus exponential 1 over the same value. So F double dash is 0.98. And then by definition, FR is the multiplication of F dash and F double dash. So we calculate the value of FR here. We call it the removal heat factor. Then the useful gain, we are going to substitute in equation 12. Q useful is the FR into aperture, into the area of the aperture, into S minus AR over AA UL TI minus TA. So FR, we have just calculated it. AA, we have calculated it in the previous slide. 430 is the falling energy into the surface. And then we're substituting the values of AR, AA, UL, and the temperature differences here. This is the temperature of the surface of the receiver, and this is the outside air temperature. So the useful energy here for this collector is 6.335 kilowatts. We can make use of that to calculate the outlet temperature. So it's just an enthalpy equation that Q useful is m dot Cp into delta T. So the delta T difference between if this is the kind of receiver that we have here, it has a certain fluid temperature in, a temperature out. So delta T is basically the difference between T out minus Tn. And Q useful here is nothing but m dot Cp T outer minus Tn. What we are looking for here, we are looking for this temperature difference. That is Qu over m dot Cp. This is Qu as we calculated it, m dot Cp, so 36. So the fluid has increased by 36.2 degrees centigrade. If it has entered with a temperature of 67.3, then the outlet temperature is basically 203.5 degrees Celsius. So we're talking about basically here an inlet or a further increase of the temperature of the fluid from 163 to a little above 200 degrees Celsius. What is being done here is just an estimation of what is going to be the average temperature drop from the outside surface to the fluid. Outside surface T, R out is the receiver outlet temperature. TF is the fluid temperature, and the difference is about 14. So we're talking about sort of an average temperature of the receiver that is 200 degrees centigrade. What is it that we are looking at here? We're looking at the changes of the outside surface temperature as we are moving from the inlet to the exit. At the inlet, we are talking about a temperature of 167.3. This is the fluid temperature here. If the difference in temperature between the fluid temperature and the outer surface temperature is 14.6, then the outer surface temperature is 167.3 plus 14.6. We can know the value of this temperature. And then the outer temperature here has a temperature difference with the outer. This is the fluid temperature leaving. It has a temperature difference between this and the surface outer temperature of the 14.6, which means that the temperature here is the outlet temperature, which is 203 plus the 14.6. The average value of the surface from this value to this is the 200 that we have used in the previous example. So this again is saying that we are able to calculate the changes in the absorber temperature as it is being extended from the inlet to the outlet of the collector that we have. Now, practically speaking, these collectors are going to be stacked together so that we have one collector followed by another collector, followed by another collector, and so on. So normally you have a series of parabolic trough collectors, and for each one of them, temperature leaving the tube in one is going to go to the other one, from the one to the other one, and so on. This can be extended over a distance that may reach to 1 kilometer. So the heat transfer fluid may take substantial amount of time to go from the inlet to the outlet. If we are looking for a constant outlet temperature, then we can control the outlet temperature flow rate. The equation that we have basically is the enthalpy increase equation, that is Q is equal to m dot Cp delta T. If you are looking for a smaller delta T, you increase the flow rate. You need a higher delta T, decrease the flow rate. And this is basically what you do to control the outlet temperature of the collector that you have in hand. So fluid flow rate is the way that we do for controlling the outlet temperature through the control of how much fluid is going to be heated inside the receiver tube, and accordingly, what will be the desired temperature that you need to reach at the end. It's a transient process as well, which means that that's something that you need to keep in mind, that it's not a certain constant value of T inlet and T outlet, but it varies as the incident radiation would vary from the early morning to the noon and then to the sunset. We're still with the optical performance of concentrating collectors. The concentrating collectors would have optical properties that may vary from geometry to geometry, and accordingly, it's not like a fixed kind of value, fixed kind of steps that we follow, but it will have some sort of a general concepts to keep or to apply for the concentrators. Although the way that we are going to determine the concentrator characteristics may vary from one to the other, but the methodology is basically generally is the same. So there's an equation for the absorbed radiation S per unit area of the unshaded aperture that can be written by this equation. IB is the beam radiation falling in. Rho is basically the reflectivity of the outer parabolic surface that reflects the radiation in. Gamma is a certain correction factor that would be considered due to the changes in the angle or the angular variations. Tau is the transmissivity, alpha is the absorptivity, and K that we have KR tau alpha is a correction factor. So the term of this equation has some simplifications that would be different from the flat plate collectors. We didn't go all that way for flat plate collectors for the estimation of the value of S. And definitely the treatment is different because of the geometry changes. The effective incident radiation measured on the plane of the aperture, IB, would include only the beam radiation, which is typically what would be expected in such application for the concentrators, except if you are talking about a very low concentration ratios, then the surface can be heated and then it's going to reflect back the heat in more than just specular. It would be even in a diffuse form of radiation there. For systems of low concentration ratio, part of the diffuse radiation will be reflected to the receiver, as I just mentioned. This amount would depend on what we call the acceptable angle of the concentrator. Rho, as I mentioned, is reflectance, is the specular reflectance of the collector. The diffuse reflectors used in cylindrical absorbed, it's going to have diffuse reflectance. If we're talking about beam reflectors, so it's the beam reflectance. So it depends on the nature of the radiation which is reaching to the surface through the reflector. If the concentrator is a refractor, then it will be the transmittant. The difference between them is that the refractor is something like a lens that passes the energy through. The reflector is a shiny surface to reflect the energy back. The next three parameters, gamma, tau, and alpha, are functions basically of the incident angle, which is theta. The effect of the angle of incidence on these characteristics can be considered individually or given by equation 741, as it will be combined with an incident angle modifier. We talked about this modifier slightly or briefly when we were considering the flat plate collector, but we did not get into that details because in the flat plate collector, it was not actually of a significant effect. Here it is because of the nature of the absorber, that it is a circular, the receiver or the reflector is parabolic in shape, so now the angle would make a difference. The intercept factor gamma is the fraction of the reflected radiation incident on the absorbing surface of the receiver. This is an expression of how gamma can be estimated. For example, if you are talking about a receiver which is extended over a certain width compared to a larger width, or what will be the effective width of the receiver to be considered, and the corresponding definition of gamma as being obtained. I'm going to go back again to the definition of gamma, that it is a fraction of the reflected radiation which is incident on the absorbing surface of the receiver. How much is the reflected radiation based on the size of the reflector and the size of the receiver, which means that there could be an effective area for the reflector and the additional area would have less significance on the reflected energy. And that's why you might be having a reflector which is limited in terms of width, and you don't need to extend the width a lot because addition of the width is not going to contribute a lot to the reflected energy. We need to reduce the heat losses. This is why we are looking at the concentrator systems. This is why we started basically from the beginning, that if we are going to go for higher temperatures, then we need to reduce the surface areas in order to reduce the losses. And this is basically what we are looking for. So you would not get higher temperature and then it will be accompanied by higher losses and you lose the kind of benefit that you are getting from going to this geometry. The receivers are usually large enough to intercept a large fraction of the reflected energy, but we need it to be effective. So the kind of energy which is going to be reflected on the receiver going for a value of gamma of 0.9 or higher is expected, but you don't get it all because basically the rest of the percentage from 90% to 100% is going to be some sort of a lower intensity borders of the images, lower intensity radiation, which is not going to affect our performance. And remember, we're trying to save as much as possible in the material. Tau is the transmissions of the cover. In the calculations, the value of tau, the value of alpha are not easy to calculate, and normally they would be, their estimation is going to be accompanied with some sort of an uncertainty. Section 7.5 is just a reading material, cylindrical absorber arrays. And here, just reminding you back again of the kind of collectors that we are focusing in here. Maybe the figure at the left here is an interesting one because it shows what we just mentioned. Look at the length of the line where the fluid as it enters from here and it extends all the way until the other side. Here we have, this is one set of collectors and then another set of collectors, a third set of collectors, so that it would not be surprising to say that the fluid has to travel over a distance that may reach to a kilometer. And as it is moving here, as its temperature increases, we have seen in the example that we have covered a while ago that at a certain point, the inlet temperature is 167 and the outlet temperature is somewhere between or somewhere above 200 degrees centigrade, which means that we can get a substantial increase of temperature through the pipe that may extend for larger distance and larger temperature that you can obtain at the end. I remember in one of the places that we have visits, they are not passing a heat transfer fluid, but they are passing water. And you enter water here as liquid at one end, and from the other end, you are getting steam, and the steam is taken into a turbine right away. Or in our visit to the SWCC in Jubail, several times we did the visit, they have some sort of a Fresnel kind of collector, which is basically similar to the one that we see in the right lower corner, which is this one. And they basically have a tube here. In this tube, there is a heat transfer fluid, some sort of an oil. This oil is being heated to an outlet temperature of about 350 or so. The length of this, of the Fresnel lens that they have used is somewhere, I think it's something like 100 meters or so. So the fluid gets in with a normal temperature, and then as it's moving in here, it passes, it ends up with an exit temperature of about 350. They take this temperature in a heat exchanger. So the oil is going to lose its heat in the heat exchanger before it comes back here again to be reheated. And in the heat exchanger, the other fluid is water, and water is being converted into steam, and the steam is used in a Rankine cycle for producing power. So it's either you would have the water turning into steam inside the tubes, or the tube can have an oil where the oil is going to be heated, and it definitely should have some oil tank in the cycle, and that would even allow for the expansion at higher temperatures, and then a heat exchanger to transfer the heat, which is gained by the oil or the fluid that passes inside the tube of the collector until the other side where it is heated to the required temperature. Look at this figure in the middle. It is showing that the receiver tube can receive energy directly from the sun, in addition to the energy which is falling into the parabola and reflected back again to the collector. So that tells that, yes, substantial heating can be occurring here, and accordingly we end up with high temperatures or temperatures that are high enough. Parabolic collectors again, and we are going to come into this specific kind of application. It's a very interesting kind of application. This one, it's a parabolic collector, but it is not a single parabola as we have seen in the previous figure. This one was basically, you can see here, you can see the parabolic shape of the reflector. like that. The other one that we have, which is we're showing here in this figure, is what we refer to as CPC, compound parabolic collector. The compound parabolic collector is going to have some sort of a parabolic shape like this, another parabolic shape like this, and you put your receiver somewhere here. So you are making a part of the parabolic shape here in this collector, and you are going to make your system as you can see it here. And this is effective in the sense that you would not have energy falling into the surface except that it has to pass by the receiver. Whatever the angle it will fall in, definitely there is a certain range of angles, and within the certain range of angles, all the energy falling into this aperture area is going eventually to reach to the receiver, as you'll see. We'll be looking at this in further details now. These are some of the applications where solar collectors are there in several places. And one of them, the one that you have at the bottom side, is what we call the solar cooker. We have been seeing in the last few years some senior exam projects that trying to come up with a solar cooker so that you would rely only on solar energy for cooking. Maybe you can look at the internet and you find that so many applications like that, especially using the Fresnel surfaces for a barbecue. So you can have a solar barbecue where basically you have some sort of a lens. And people were showing very interesting videos, by the way, like, I mean, your generation, you did not see the overhead projector. Previously, something like a couple of decades ago, the overhead projectors was very common way of using it for presentations and the lectures. The PowerPoint presentations and the computers and screens were not very famous, did not find their way into the universities and schools because of their very high price. So instead, or previous to this technology, there was the overhead projector, where we get some sort of transparent papers. You put it on the projector, and the projector reflects that into the wall. And then the paper can be printed, or we can write by colored markers on it, and then you can see the writing occurring instead of writing on the board. That used to be a way to do that. This kind of overhead collectors used to have some sort of a light source, and on top of the light source is basically a transparent piece of glass, and then a reflector that reflects this writing on the wall. This piece of glass is basically some sort of a Fresnel lens. Actually, we used to go to the audiovisual department here in the university and borrow some of these glass sheets of the old projectors that are being broken. And we use this for concentrating the solar energy. You might be lucky to see one of the applications I recall I've seen in a YouTube video that was showing somebody has gone to the used electronics markets, and he bought one of the very old television sets, TVs, that has a flat glass screen. The flat glass screen is nothing but a Fresnel lens. And he used that in making a system that can boil water or can do some sort of a barbecue. So these are some of the practical applications that are even easy to build, and it fits many places, especially with countries that have problems in energy, and solar energy is a good a good substitute. Look, for example, in the middle of Africa and basically countries that are close to the equator. Look at the upper left figure, where basically this is water, and you can do boiling water for whether it's for cooking or for preparing a hot drink, and that's something that can be utilized. And these are collectors on the right side that are sold in a local market, where there is a stand here. In that stand, you can put your pot, where the pot could be either water or food that needs to be cooked. So these are some of the practical and cheap applications that are doable for utilization of the solar energy in everyday life of different families. On the other hand, this is some of the sophisticated kind of applications that we're talking about. A Rankine cycle system here, large number of mirrors are there, and they are reflecting the energy on the top of each one of these towers where there is a large tank. The tank is receiving this reflected energy. It has water inside. Water is converted into steam. So this tank basically is nothing but a boiler or a steam generator where steam is being formed and the steam can be taken to run a turbine and then you can generate electricity using this kind of arrangement. It can be either given in a form of an arc like the upper figure, or in the down figure, you can find that the mirrors are making a whole circle around the receiver here. Parabolic trough collectors is something that you can see. Actually, right now you don't only see this, but you can see parabolic trough collectors and you can see even PV panels. A couple of days ago, there was a grand opening of a PV plant in Sakaka that can produce something like 400 megawatts of electricity. But that's another technology. It's not for heating, but it's for PV, for just producing electricity. And you have covered that already in another course of the same concentration that you are in. The mirrors reflecting their radiation into a tower is in the left upper figure. So these figures are being left with you here so that you can have a look at it and just see some of these applications that we are using for solar energy utilization. Any questions so far? If not, then we are going to get into another application which is related to the utilization of solar energy that will be focusing on the parabolic or the compound parabolic collectors, which are having or found their way into the market and being spreadly used lately. So we're still with the concentrating collectors, and we're talking about the construction of collectors that can function either seasonally or annually with minimum tracking. So the idea behind coming up with the CPC or the compound parabolic collector is to avoid tracking. Why do we need to avoid tracking? Because of two things. Number one, mechanically, it's a complicated system. You have to build the system. You have to control it so that it will track the sun in the sky. And this tracking, we talked about tracking last time, it can be manual, it can be automated. And if it's automated, you can do it with correction parameters. That's something that can sense the solar radiation and just sense its feedback for the motor to move, and or it can be done manually. So this kind of thing, it adds a sophistication, a mechanical motion, and definitely it's going to add to the price of the system that you are using. If you can build a system that would not require tracking and yet can absorb substantial amount of energy, then that would be great. And that was basically the motive behind coming up with this type of collectors. Tracking is not only the issue of being complicated because of adding a mechanical component, which will come up with its price, with its maintenance issues, with its precision issues. But we've seen in the previous example that even it has, because it's a stand, it is made of metal. So there's some sort of conduction losses through the heat are going through that as well. So going for a system that would not require to be integrated into a tracking system is something that it is worth considering and looking for. Non-imaging concentrators have the capability of reflecting to the receiver all the incident radiation on the aperture. You can imagine that. All radiation falling into the aperture are going to reach for the receiver without having to do tracking for the sun. Definitely, this is going to be, nothing is perfect. So this is going to be done within a certain incident angle, but it may have wide limits. These limits are defined by what we call the acceptance angle of the concentrator. All the radiation incident within the acceptable angle is reflected on the receiver. So you don't have this kind of losses here. You don't have to rotate it to follow the sun. It's just you would know that any radiation which is being intercepted within the acceptance angle is going to fall into your receiver. Most of this section that we have in is dedicated to the compound parabolic concentrators or collectors. This is basically what we are considering. So correctly, it would be compound parabolic concentrators. Why compound? Because it's not a single parabola. And look at the left side figure, and you'll see here, what you can see here is basically this is a part of a parabola here, which is this. But you are not considering the whole parabola. You are just, the whole parabola, I mean that the surface is being extended like this. And the other one is going to have a surface which is extended like this. But we don't need all of that. We just need a piece of it here. You start from a certain point and you end up where part of the parabola that is parallel to that axis. So what length of the parabola we're going to stop at? We're going to stop whenever the parabola is reaching to be closer to being parallel to this. And the second one this way. And then the rest is not needed, and you put your receiver here. Is it going to be useful? Look at the right side figure here, and we'll tell you that within this acceptance angle, this is the acceptance angle that you can see here, that which is in the left figure, it is extended from here to here, from this to this. This is basically to this. So any radiation which is falling into the surface within this angle is going to reach to find itself into the receiver. And how this is being done, it is shown here in the right figure, that all the energy falling is basically falling and reaching this. Definitely, if the radiation is coming with a different angle like this, it will be reaching here, or basically reaching here, and reflected here, or reflected here, or reflected here. So basically, this is receiving all kind of radiation falling through the aperture, which is the opening that we have here. Any thermal radiation that would pass through the aperture, whatever its angle, as long as it is within that acceptance angle, is going to fall into the receiver. This is great, and you don't need to have a tracking system with it. So that's why there has been great interest, I mean, practically speaking, about the compound parabolic concentrators. You don't need to have a tracking system with it, and accordingly, its price is not going to be too high as you might encounter in parabolic trough collectors with a single tracking axis, or sometimes a double tracking axis, which would make it further more expensive. What are the limitations here? They are non-imaging, so you don't expect higher concentration ratios. You do not get it here. Usually it will be less than 10. If you need more than 10, then you have to go for the other types then. So these concentrators are potentially useful as linear or trough type collectors. And the following analysis that we're going to do is basically considering two-dimensional concentrated parabolic or compound parabolic concentrators. Each side is a parabola, as I just mentioned, and we are combining two types of parabola, especially in a special way that it will be at the end looking like it's like a barrel, as you can see it here. So what we have here on the right side, this is a part of a parabola, and the left side is another part of a parabola, or a part of another parabola. And you are combining this piece of the parabola and this piece with the absorber surface that you find here at the bottom. So it's not a single parabola as we see in the parabolic trough collectors, as we did in the previous part of the chapter. The angle between the axis of the CPC and the line connecting the focus of one of the parabolas with the opposite edge is the acceptance half angle. What we mean here is, back again, this is the angle between this axis of the CPC and the distance that's going to extend from the edge of this receiver, passing by the focal point into the edge, the upper edge of the collector. So this angle between this line and the center line is basically the acceptance half angle. If the reflector is perfect, any radiation entering the aperture at an angle within the acceptance angle is going to be reaching to the receiver. It will be reflected to the receiver. Nothing is perfect, which means that you can find some of the reflectors that would not have 100% of the energy in, maybe due to some sort of surface defects or some surface issues. But otherwise, ideally speaking, with this kind of geometry, any radiation beam which is falling within that acceptance angle is going to reach to the surface, to the absorber surface. The concentration ratios can be given here, and the concentration ratio for our case is 1 over sine theta c. Theta c again is the acceptance angle. So that if you have an acceptance angle of 23.5, then you are going to have a concentration ratio of 2.5. If the acceptance angle is 11.75, then the value of the concentration ratio is going to be almost close to 5. So now it depends on how much you are designing your acceptance angle, and accordingly you can expect how much is the concentration ratio that you are going to get for your system. In this figure, we're talking about the case of ideal versus non-ideal cases. This is basically a representation of the fraction of radiation falling into the aperture at an angle theta, which reaches the absorbers as a function of this angle. How much of the energy that will fall into the aperture reach to the collector receiver, you can see it here. For the case of ideal case, you're going to have a ratio of 100% of the energy is falling into the receiver, as the value of theta is going to be varying from 0 up to the acceptance angle limit. So for the case of full CPC with no surface errors, you are going to get all the energy which is passing by the aperture falling into the surface. This is the ideal case where they have no surface errors. And in some cases, they would, just for the sake of optimizing the manufacturing of this unit, would say that, do we really require the whole length of the unit like this? Do we have to go for all that length? Actually, most of the energy can be receiving, like maybe 90% or more of the energy can be received if you are talking about a shorter CPC. They call it truncated CPC. So they don't go for the whole height, but they go for a fraction of the height, and they call it, it's a truncated collector. And this is part of what you can see here, that if you are talking about a truncated collector with a CPC, you can find that you can still get some radiation falling into the surface, even if you exceed the value of the acceptance angle. If you have surface errors, then the picture is not going to be exactly as ideal as you can see it here. A value of the fraction of the energy falling 100% is going to fall into the to the receiver until the value of theta c. But if there are some sort of surface errors, then you can start having the value being diverted a bit from the ideal. And this is what's been given here by the dotted line. So we're talking about three cases here. The solid line is the ideal case. The dashed line in case of having a truncated collector. And the dotted lines is the one that represents the case. What if we have some sort of errors in the surface? So for real CPC with surface errors, some of the radiation incident on the angle can reach less than, or actually less than theta c does not reach the absorber, which is covered by this fraction here. There's some amount of energy is not reaching the absorber. Why is that? It is because of having some errors in the surface finishing. And actually, when you exceed the value of theta c, you can still see that some of the radiation is still reaching on the surface. So it is not as sharp as the case of a perfect surface. Here we're talking about the idea of a truncated collector. Look at this. This is the full length of the collector, and this is the truncated collectors. And in the case of truncated collectors, yes, you are going to receive a total of less amount of radiation on the receiver surface, but it is not significantly less. So economically speaking, you can cut a part of the height of the collector, save material without losing too much of the falling energy into the receiver. I'm going to stop here and then we can pick it up from here in our next class, inshallah. Just a little announcement I would probably make before you leave the class is that already homework number 6 is there in the Blackboard. This is one thing. And the second thing is that let's have a third quiz next Wednesday. The quiz will be on chapter 6. So far we had 2 quizzes. And we said that we need to have more quizzes. So a third quiz is going to be on Wednesday, which is, I'm expecting everyone to join. And the last day of classes is going to be the following Monday. And on that Monday, I'm going to make an optional quiz so that if you feel that you have done good enough in the quizzes, in the 3 quizzes, the 2 that we have earlier and the one on Wednesday, that will be fine. You don't have to take the last one. If you need to improve your grades in the quizzes, then you can take the last one. And then what I would do, I will look at the 4 quizzes, pick the best 3 values and discard the lowest one. So that's the plan so far. And a week from today, on Wednesday, we'll be having our third quiz again. As I mentioned, it will be covering chapter 6, inshallah. So that's it for today. You have any questions or any comments?
Doctor, Monday, you mean 26?
Monday, 26, the last day of classes, it will be an optional quiz.
How
Yes.
we have classes in the final day exam?
26 is the last day of classes.
But I have a final exam in 26.
You would ask the registrar, not me. I mean, he's the one who put that, who put this modifications, and that actually has been done just to cope up with the issue that finishing everything before the Eid, so or before Ramadan ends. That's something I cannot do anything about it. I'm sorry about this. But I mean, even for the normal semesters, the way that we used to have a full semester, sometimes you would, I used to have this before in our department or even across the university. The last day of classes, you can have an exam, but the exam used to be something like a drawing, like 210 or so. I don't know what kind of exam that you have on 26. What material, what subject?
I have GS in 26 and 27 we have the CH424.
Oh, I see. Well, you need to manage your time then. That's the only thing I can tell you. Good luck with it. If you wish to schedule our optional quiz at a different time and you agree on it, all of you, I don't mind. It's fine with me. If you are interested in the optional one anyway. Any further questions? If not, then